Greetings, class, and welcome to our new unit. Unit 2, Biochemistry, the Chemistry of Life. Biochemistry is a combination of two words, just like so many of our other science words, bio and chemistry, life and the study of matter. In this particular unit, we're going to look a bit at chemistry, a little bit about water, some acids and bases, we're going to talk about compounds, and we're going to talk about macromolecules and enzymes. So quite a bit of information we'll be covering in this particular unit. So let's start at the beginning with the study of matter. What is matter? Matter is anything that has mass and takes up space. The building blocks of matter are atoms. The word atom derives from the Greek word atomos, which means uncuttable. And that was kind of an appropriate view of the atom for hundreds of years, as that's the smallest particle that humans envisioned could exist in matter. Of course, nowadays we know there are even smaller particles that make up the atom. We call those subatomic particles, and they include things like protons, which have a positive electrical charge, neutrons, which have a neutral charge. Both protons and neutrons are found in the nucleus of the atom, and electrons, which have a negative charge, are found in the electron cloud, orbiting around the nucleus. The vast majority, practically all of the mass of the atom is found within the nucleus itself. And outside of the nucleus, the electron cloud is pretty much mostly empty space, with the electrons swirling around. To start our study of chemistry and how it relates to what we'll be doing in biology class, we need to take a few minutes to review the periodic table. The modern periodic table was developed about 150 years ago by Dmitry Mendeleev, a Russian chemist. Although he didn't have nearly as many elements as we have today, his periodic table is remarkably like ours. Although his was arranged by order of increasing atomic mass, or what they called increasing atomic weight back then, our modern-day periodic table is organized by increasing atomic number. Now, a few trends I want to notice with you on the periodic table include the fact that the periodic table is organized into 18 groups or families. Those are the vertical columns like these that I'm highlighting. Elements within the same group or family have similar properties, and why they have those similar properties we'll explain in a minute. Horizontally, you have 7 different rows or periods. These elements can vary dramatically as you move from one side of the periodic table to the other. However, each one of the elements within the same period have the same number of energy levels for their electrons, as indicated by the number on the left-hand side of the table. The periodic table is organized into a few different groups. On the left-hand side, you have the metals. On the right-hand side, you have a few more metals, the metalloids, and then the nonmetals over here on the right-hand side. Down at the bottom, we have the lanthanides and actinides, or the rare earth metals. Moving from left to right in the periodic table, we have some interesting trends. We have what are called the representative elements on the very right here and the very left here. Those elements follow the rules of the periodic table the best. Then in the middle of the table, you have the transition elements. These particular elements don't follow the rules quite as nicely, and they do, as the name says, transition the elements as you move from metals on the left-hand side to metalloids and nonmetals on the right-hand side. Within an individual box in the periodic table, you can get a lot of information. First, you can get the atomic number, which tells you the number of electrons and the number of protons in a particular element. You can also get the atomic mass, which is the average of all the different forms of a particular element. We call the different forms of a particular element isotopes. Isotopes are atoms of the same element that have different numbers of neutrons. So consequently, they have slightly different atomic masses and sometimes different properties as well. The atomic number and the mass number can be used to derive the number of neutrons in a particular element by calculating the mass number. The mass number is simply the sum of the number of protons and neutrons, and it's usually derived by rounding the atomic mass to the nearest whole number. So for example, carbon's mass is 12.01, but if we were to round it to 12, that would be the mass number. And if you were to take the 12 and subtract it by the atomic number, which was 6, you would end up with 6 neutrons. The electrons are derived by the atomic number as well, so they're the same as the number of protons. Here's a great example of carbon again, but now we have the model that we can see of the carbon atom. We can see the nucleus, which contains the 6 protons and neutrons, and then orbiting around the carbon nucleus are your electrons in the first energy level. There are 2 electrons, and then the outer energy level, there are 4 valence electrons. Valence electrons are those electrons in the furthest energy level of the element, and these are the ones that are involved in reacting with other atoms. This Bohr model here, you can see what's also known as the planetary model of the atom, is a rather simplified view of the atom because it assumes that the electrons are always found in these static orbital shells or energy levels, which is not always the case. As you can see in the bottom diagram, this is probably a better representation. Generally, the electrons are found somewhere in the electron cloud, but not necessarily always perfectly in these specific energy levels. But we use the Bohr model because it helps us with our understanding of the periodic table and why things are positioned in the groups they're in, and also why they're in the periods that they're in. If you were to look at carbon on our periodic table, you would see carbon is in row 2 and has 2 energy levels. As we mentioned in the previous slide, valence electrons, again, are those electrons involved in the interaction during a chemical reaction. That's these electrons here, the ones on the outer energy level. These are the ones that are most important when you're dealing with the creation of compounds. What are compounds? And why are compounds different than mixtures? Compounds are actually pure substances, just like elements. They have their own specific properties, whereas mixtures are different. Mixtures are just physical arrangements of material. They're sharing the same space. They may be in contact with each other, say, for example, trail mix or a bowl of raisin bran, but the substances that are in the vicinity of each other are not actually combined together chemically. They can be separated out and they retain their own individual properties. Compounds, however, are different. In a compound, elements combine together chemically. They give away their original properties and they take on new properties together in that compound form. A great example I have listed below here is sodium chloride, NaCl. Sodium is a very dangerous metal, chlorine is a very dangerous gas, and yet combining together chemically, they create a substance we need for life. Compounds are always in definite chemical proportions. For example, water is always H2O, and they're represented using formulas like, for example, iron oxide, Fe2O3. Now, what holds a chemical compound together are the chemical bonds, which makes them different from mixtures. There is no bond holding together a mixture. It's the chemical bond that holds the atoms together that creates the new substance, which has its own properties and why it's considered a pure substance. There are 2 main types of bonds we're going to be talking about: ionic bonds and covalent bonds. And then there are also some weaker attraction forces that exist between molecules that we'll be looking at today and in our next lesson: van der Waals forces and hydrogen bonds. Let's first start talking about what every good atom wants. Every atom dreams, hopes, wishes to have a full outer shell. They call it the octet rule, and all atoms dream of being stable. Only one group of elements, the group elements in group 18, the noble gases, have a full outer shell. All the other atoms on the periodic table, all the other elements, have to either find electrons or give them away so that they can achieve this goal of a full outer shell. Atoms can transfer electrons or they can share them to achieve this full energy level. When atoms transfer electrons or share them, they become attracted with a chemical bond. Let's start looking first at ionic bonds. Ionic bonds are compounds that result by the formation of ions. Ions are atoms that have electrical charges. Now, how does an ion form? In this case here, we have a metal sodium and a nonmetal chlorine. Sodium, which is a metal, has very few valence electrons. Chlorine, which is a nonmetal, has many valence electrons, as you can see here. Metals are traditionally electron donors because it's easy for them to give away 1 or 2 electrons and drop an energy level than it is to try to gain 6 or 7. Nonmetals are traditionally electron takers because they're always generally 1 or 2 electrons short of a full outer shell, and it's easier to find 1 or 2 than to get rid of 7. So as you can see in this example here, sodium could very easily give away 1 valence electron to chlorine, and chlorine would be very receptive to take it. And in doing so, they would create ions. The formation of these ions creates oppositely charged particles, as you can see here in this next slide. These oppositely charged particles are what creates the ionic bond, because now you have positive and negatively charged substances, like so much in nature, opposites attract. The oppositely charged particles will attract to each other, and they will create an ionic bond, and a new pure substance will be formed. In this case here, you can see the sodium metal, the chlorine gas, and the table salt that forms, completely different than the components that make it up, simply by the transfer of this one valence electron. As I mentioned in the previous slides, an ionic bond is formed when one or more electrons are transferred from one atom to another. Generally, ionic bonds result from a chemical compound that forms between a metal and a nonmetal. These substances are frequently referred to as salts, and in fact, elements in group 17, halogens, the name halogen literally means form salt. Here's a great example of what we talked about a few moments ago. The sodium ion here taking on the positive charge, the chlorine becoming negative. Why does the sodium become positive? Because it gave away an electron. By giving away an electron, it now has more protons than electrons. Chlorine becomes negative because now it has more electrons than protons. Metals become positively charged ions and ionic compounds, whereas nonmetals will become negatively charged. Another type of bond is called a covalent bond. A covalent bond is different because in a covalent bond, rather than transferring the electrons are shared. Isn't that beautiful? Isn't that what we all taught when we were in kindergarten? Sharing. So it's subtly different. Let's look at it closely here. Here's an example of hydrogen. This is an example of what we call a diatomic molecule. A diatomic molecule is when you have two atoms of the same element, and they become chemically bonded together. So you can see, for example, this is H2. It is two hydrogen atoms which have become chemically combined to form a molecule of hydrogen, H2. This is an example of a covalent bond. Each hydrogen has one valence electron. They can share them together, and now they have two. Here's another example of a diatomic molecule, oxygen, O2. They're sharing those valence electrons and creating a full outer shell. When you have two or more atoms held together chemically by a covalent bond, we call that a molecule. A molecule is the smallest substance of a covalent compound that still retains all the properties of that particular substance. A great example is water, H2O. This is one molecule of water. This is still water. It has all the properties that a glass of water would have or a pool of water. It is still a water molecule, and it is still water. Anything less than this would involve breaking the bonds between the hydrogens and the oxygens, and then you would no longer have water, because water is H2O. Remember, definite chemical proportions, definite chemical formula, and composition with the elements. Some other interesting forces and phenomena in nature that we're going to look at include the van der Waals force, and then in our next lesson, the hydrogen bond, which is a very significant bond because it helps with the creation of water molecules. Let's close out by looking at a van der Waals force because it's pretty interesting. The van der Waals force occurs when you have electrons that are built up, not necessarily equally in different places. This movement of electrons from one place to another can create an imbalance, which can create charges. And these charges, negatively charged buildup on one side, positively charged on the other side, can create an attractive force. It's weak and temporary, but it does allow for cool things to take place. Like, for example, a gecko being able to stick to glass and climb up a glass or a wall. They're not as strong as the forces that we mentioned before within an ionic bond or a covalent bond, but they are interesting, so I thought I'd mention them to you. When we meet again, next time, in our second lesson, we'll talk about water, probably one of the most unique substances on planet Earth. It has a fascinating structure and has many exciting things that go on within the water molecule itself and the molecules of water together.